Yes, so the next talk will be given by Naoki Kitazawa, and it's called Explicit Construction of Explicit Real Algebraic Functions and Real Algebraic Manifolds via Reeb Graphs. Please.
Okay. Thank you for your introduction, and thank you for such a nice opportunity, and thank you for joining my talk. I'm Naoki Kitazawa from Institute of Osaka Central Advanced Mathematical Institute and Institute of Mathematics for Industry, Kyushu University from Japan. Today, the title of my talk is Explicit Construction of Explicit Real Algebraic Functions and their algebraic manifolds by the Reeb graphs. If you have a question, please stop me. Okay, let's go. And this slide is on grants supporting our study. Okay, let's go. And I want to present shortly about the algebraic functions and maps. According to Nash, followed by Tugnori, for example, a smooth closed manifold is regarded as a non-singular real algebraic manifold, which is also a real algebraic set. Existence theory of real algebraic manifolds and real algebraic maps have been well known, and we can easily attain such objects and molecules by approximations. For example, whereas it is very difficult to know explicit structure is very difficult. Of course, some specific examples are well known. For example, canonical embeddings and projections of spheres in Euclidean spaces, and more generally, more functions on E groups and symmetric spaces, for example. Okay. However, it is very difficult to know global structures and properties. Okay, let's go. Today, I want to. Now, let's go. As one problem, today I want to challenge problem one. First, can we obtain real algebraic functions of imaginary maps in constructive ways? Can we know their precise global structures and properties? For example, can we know about privilege? As another, can we know about the real polynomials for the zero sets and the real algebraic manifolds? And we present some of our explicit answers. Okay. Then we challenge problem to map precisely. Excuse me, which may be only presented in a bit different way. Can we have real algebraic functions whose privilege is satisfied suitably given conditions of smooth and non-singular real algebraic manifolds and no information on important real polynomials for the zero set, etc. Okay. Next. And these programs are originate from Charcot's famous problem. The problem is, can we have a smooth nice function or smooth category? In the smooth category, have a nice function whose Reeb graph is isomorphic to a given graph. What is the Reeb graph? The Reeb graph of a smooth function is a natural graph whose underlying space is the natural constant space of the manifold consisting of all components of privileges. Okay, let's show examples of Reeb graphs. There are functions, natural functions on spheres and atolls embedded naturally in the three-dimensional space and considered, and the functions are obtained as by considering natural heights. For these, the Reeb graphs are only a graph with one edge, and a graph is exactly 4 edges and 4 vertices. Okay. And such objects are important in knowing structures of global structures of manifolds. And related to this program, some answers have been given. Of course, Charcot has given answers on closed functions on closed surfaces, and data, Masumoto-san and Professor Saeki, who has been my first professor for 3 or 4 years, has given an improvement of the result of Shalko for arbitrary finite graphs. Data, Dr. Misharaku, maybe he's here to consider the most functions on closed manifolds. And my problem is the following. Can we have a smooth nice function whose preimage is a homeomorphic to preimages with no singular points are homeomorphic to prefixed manifolds? This is my devised problem. The original program. And we consider these programs in the real algebraic category. Okay? As a new problem. Okay, I would like to explain about fundamental notion of smooth manifolds and related notions. First, alge is the k-dimensional Euclidean space. A simplest smooth manifold, a Riemann manifold endowed with the standard Euclidean metric and a non-singular real algebraic manifold, k-dimensional real algebraic space. And this denotes the distance between P and the origin. The SK and DK plus 1 denotes the k-dimensional unit sphere and k plus 1 dimensional unit disk. And XL is an L-dimensional manifold X. L in XL is for the dimension. Okay? And this is the map defined by, in this way, canonical projection. And the restriction to the unit sphere is called the canonical projection of the unit sphere. For a smooth map F between two manifolds, smooth manifolds, a point in the manifold of the domain is a singular point if there the rank of the differential is smaller than both small m and small n. SP is also called the singular value of F, small f. Large SF denotes the set of all singular points of F. A smooth function is called a most function if it is smooth and at its singular point identified with the origin, it is represented as a map of the quadratic form plus FP for some integer. And two smooth manifolds are diffeomorphic if there is diffeomorphism, a smooth homeomorphism with no singular points from one manifold to the other. Okay? Okay. I would like to explain about an algebraic domain. Let small k be an integer greater than 1. An algebraic domain in the k-dimensional affine space is a bounded open set such that the closure is surrounded by a finitely many mutually disjoint connected non-singular real algebraic fiber surfaces. The Sj, each Sj is a connected component of the zero set of a polynomial. For each j from 1 to L, the complementary set of Sj in the zero set is, and the closure of UR, it is the closure of a sufficiently small open neighborhood UR of the closure R of R do not intersect. This is one of simplest algebraic domains in the plane, surrounded by circles of fixed study. Dots are for abbreviation. This is for the Reeb graph of a smooth function. One of important theorem is the following. It's shown by Professor Saeki. For a smooth function on a closed manifold such that the singular value set is finite, then the cosine space is a graph. And whose vertex set consists of all components containing some singular points. And WF is the Reeb graph of F, and QF denotes the cosine map. This is the Reeb graphs of the natural functions again. Not that they are also examples of most functions. Okay? Okay, let's go. As a similar and different notion, we like to introduce the pancreative graph of an algebraic domain. The pancreative graph of the algebraic domain is defined in the following way. The graph is the natural constant space of the closure of the region and the algebraic domain consisted of all components of pre-images of the function obtained as the restriction to the of the canonical projection to the closure of the domain. And the vertex set consists of all components containing some singular point of the function obtained as the restriction of the canonical projection to the boundary. Okay. This shows the pancreative graph of a domain, such a domain. Okay. Surrounded by dots. Dots are for application. Okay. Okay, let's go. And I'd like to show a main result. Let small m, small k be positive integers. And algebraic domain is represented as the intersection of the small neighborhood of the domain and the point giving making the polynomial positive. The algebraic domain is represented as this. Then, for the pancreative graph of GR, there exists some non-singular closed algebraic manifold assumes their algebraic function and whose Reeb graph is isomorphic to the pancreative graph. And the figure in the previous slide, etc., shows a simplest example. Okay. This is also the Reeb graph of some algebraic function shown on a closed manifold. The algebraic manifold. Okay. I'd like to show a proof. In the first step, we define the zero set as this. And after that, we see that this is the union of finitely many components of the zero set of the real polynomial in the real affine space, and it is also a non-singular closed real algebraic manifold. For this, we can apply implicit function theorem. And after that, we put the desired manifold as define the desired manifold by as large S and desired function by the composition of the restriction of the canonical projection to the manifold and another canonical projection. And this is for pre-images of some points of R points in the region. For the map into onto R. For example, in the case R is the interior of the unit disk, then we have a canonical projection of the unit sphere as this. Okay. And I want to remark some. Maybe there are some. In general, topologically, we have so-called special generic maps as the maps onto the image closure of the domain. Special generic maps are generalizations of most functions with actually two singular points of spheres and canonical projections of unit spheres. They are very low to be nice classes of generics with mapping, knowing the topologies and the differential structures of the manifolds. By the definition, the manifolds and the maps are strongly restricted, and on the other hand, some manifolds regarded as elementary in some senses. For example, such connected sum admits such maps in considerable cases. thanks to such interesting properties, there are many studies on special generic maps. Okay. And arbitrary maps. According to a study by Bodin, Professor Bodin, Popx Pump, and Soria-san, maybe she's here. For the other and she's that. She's also the speaker. For the wicked obeying in the plane and pancreatic graph of certain wide class, we have a station as presented in theorem 2. Okay? However, we can't know the polynomial polynomials for the curves surrounding the domains explicit in general. As another debug, for a generic so-called generic graph, we have a most function such that the distinct between the values are distinct, and the Reeb graph is isomorphic to G. A suitable approximation presents a smoothly algebraic function. However, we can apply this for graphs which are not generic. On the other hand, we don't use such technique and we avoid approximations and existence. Okay? And as another answer is this. We give L and M, small m and small m integer, positive integers and increasing sequence of length f. There are of length f. This is a family of smooth closed manifolds such that they are sometimes unit spheres and sometimes collected sum of the products of two unit spheres. Collected sums. And under such a situation, we have a similar result. Furthermore, the singular set is finite, and this is the set. That sequence is the set of all singular values. And the preimage is diffeomorphic to small fj for a point in the interval, open interval from tj to interval. And and comments. I want to comment on theorem 3. Okay. Main gradient of our proof of this theorem 3 is, in short, using technique of theorem 2 inductively. Okay. By using theorem 2, we can have a map on a closed manifold into the map into the domain. And we can also have another domain whose boundary is the obtained manifold and finitely many disjoint disks and disjoint spheres of fixed value. And that's we compose the canonical projection. This construction is the differomorphic to unit sphere or manifold represented as collected sum of two unit spheres. Okay? And this is the previous result related to theorem 3. There is a okay. Small m be an integral greater than 2, and there's a graph, and on a graph there's a continuous function. And family of smooth closed manifolds available by H are given. And manifolds satisfy the condition. And then under this condition, we have a most function on some manifold. And the Reeb graph is identified with the given graph. And the preimage is as prescribed. In fact, manifolds are more generalized there. Okay. Okay, I'd like to close that talk. And by future problems. First, can we extend our answers to problems of results to graphs of either classes and cases conditions on preimage are more general. It seems to be difficult because the category is very strict. And another program for graph, what is the simplest and most natural smooth function whose Reeb graph is the graph in the manifolds? We may also need to pose suitable condition singularity, preimage, and the category. A kind of natural programs. And for a graph with exactly one edge and tubularities, the canonical projection of unit of set seems to be an answer. Okay. Differences. Okay. Thank you for your listening.
Thank you very much for the talk.
you see that?
Yes, so the next talk will be given by Naoki Kitazawa, and it's called Explicit Construction of Explicit Real Algebraic Functions and Real Algebraic Manifolds via Reeb graphs. Please.
Okay. Thank you for your introduction, and thank you for such a nice opportunity, and thank you for joining my talk. I'm Naoki Kitazawa from Institute of Osaka Central Advanced Mathematical Institute and Institute of Mathematics for Industry, Kyushu University from Japan. Today, the title of my talk is Explicit Construction of Explicit Real Algebraic Functions and their algebraic manifolds by via the Reeb graphs. If you have a question, please stop me. Okay, let's go. And this slide is on grants supporting our study. Okay, let's go. And I want to present shortly about the algebraic functions and maps. According to Nash, followed by Tugnori, for example, a smooth closed manifold is regarded as a non-singular real algebraic manifold, which is also a real algebraic set. Existence theory of real algebraic manifolds and real algebraic maps have been well known, and we can easily attain such objects and molecules by approximations. For example, whereas it is very difficult to know explicitly, explicit structure is very difficult. Of course, some specific examples are well known. For example, canonical embeddings and projections of spheres in Euclidean spaces, and more generally, more functions on E groups and symmetric spaces, for example. Okay. However, it is very difficult to know global structures and properties. Okay, let's go. Today, I want to. Now, let's go. As one problem, today I want to challenge problem one. First, can we obtain real algebraic functions of marginally maps in constructive ways? Can we know their precise global structures and properties? For example, can we know about privileges? As another, can we know about the real polynomials for the zero sets and the real algebraic manifolds? And we present some of our explicit answers. Okay. Then we challenge problem to map precisely. Excuse me, which may be only presented in a bit different way. Can we have real algebraic functions whose privileges satisfy suitably given conditions of smooth and non-singular real algebraic manifolds and no information on important real polynomials for the zero set, etc. Okay. Next. And these programs are originate from Charcot's famous problem. The problem is, can we have a smooth nice function or smooth category? In the smooth category, have a nice function whose Reeb graph is isomorphic to a given graph. What is the Reeb graph? The Reeb graph of a smooth function is a natural graph whose underlying space is the natural quotient space of the manifold consisting of all components of privileges. Okay, let's show examples of Reeb graphs. There are functions, natural functions on spheres and atolls embedded naturally in the three-dimensional space and considered, and the functions are obtained as by considering natural heights. For these, the Reeb graphs are only a graph with one edge, and a graph is exactly 4 edges and 4 vertices. Okay. And such objects are important in knowing structures of global structures of manifolds. And related to this program, some answers have been given. Of course, Charcot has given answers on closed functions on closed surfaces and data Matsumoto-san and Professor Saeki, who has been my post professor for 3 or 4 years, has given an improvement of the result of shell co-fibratory finite glass. Data, Dr. Mishalak, maybe he is here to consider the most functions on closed manifolds. And my problem is the following. Can we have a smooth nice function whose preimage is homeomorphic to preimage with no singular points are homeomorphic to prefixed manifolds? This is my devised program, the original program. And we consider these programs in the real algebraic category. Okay? As a new problem. Okay, I would like to explain about fundamental notion of smooth manifolds and related notions. First, RK is the k-dimensional Euclidean space. A simplest smooth manifold, a Riemann manifold endowed with the standard Euclidean metric and a non-singular real algebraic manifold, k-dimensional real algebraic space. And this denotes the distance between P and the origin. The SK and DK plus 1 denotes the k-dimensional unit sphere and k plus 1 dimensional unit disk. And XL is an L-dimensional manifold X. L in XL is for the dimension. Okay. And this is the map defined by in this way, canonical projection. And the restriction to the unit sphere is called the canonical projection of the unit sphere. For a smooth map F between two manifolds, smooth manifolds, a point in the manifold of the domain is a singular point if there the rank of the differential is smaller than both small m and small n. SP is also called the singular value of x, small f. Large SF denotes the set of all singular points of f. A smooth function is called a most function if it is smooth and at its singular point to identify with the origin, it is represented as a map of the quadratic form plus FP for some integer. And two smooth manifolds are diffeomorphic if there is diffeomorphism, a smooth homeomorphism with no singular points from one manifold to the other. Okay? Okay. I would like to explain about an algebraic domain. Let small k be an integer greater than 1. An algebraic domain in the k-dimensional affine space is a bounded open set such that the closure is surrounded by a finitely many mutually disjoint connected non-singular real algebraic hyper surfaces. The Sj, each Sj is a connected component of the zero set of a they are polynomial. For each j from 1 to L, the complementary set of Sj in the zero set is, and the closure of UR, which is the closure of a sufficiently small open neighborhood UR of the closure R of R do not intersect. This is one of simplest algebraic domains in the plane, surrounded by circles of fixed study. Dots are for abbreviation. This is for the Reeb graph of a smooth function. One of important theorem is the following. It's shown by Professor Saeki. For a smooth function on a closed manifold such that the singular value set is finite, then the cosine space is a graph, and whose vertex set consists of all components containing some singular points. And WF is the Reeb graph of F, and QF denotes the cosine map. This is the Reeb graph of the natural functions again. Or not that they are also examples of most functions. Okay? Okay, let's go. As a similar and different notion, we like to introduce the pancreative graph of an algebraic domain. The pancreative graph of the algebraic domain is defined in the following way. The graph is the natural cosset space of the closure of the region and the algebraic domain consisted of all components of pre-images of the function obtained as the distribution to the of the canonical projection to the closure of the domain. And the vertex set consists of all components containing some singular point of the function obtained as the distribution of the canonical projection to the boundary. Okay. This shows the pancreative graph of a domain, such a domain. Okay. Surrounded by dots. Dots are for application. Okay. Okay, let's go. And I'd like to show a main result. Let small m, small k be positive integers. An algebraic domain is represented as the intersection of the small neighborhood of the domain and the points making the polynomial positive. The algebraic domain is represented that this. Then, for the pancreative graph of GR, there exists some non-singular closed algebraic manifold as smooth algebraic function, and whose Reeb graph is isomorphic to the pancreative graph. And the figure in the previous slide, etc., shows the simplest example. Okay. This is also the Reeb graph of some algebraic function on a closed manifold. The algebraic manifold. Okay. I'd like to show a proof. In the first step, we define the zero set as this. And after that, we see that this is the union of finitely many components of the zero set of the real polynomial in the real affine space, and it is also a non-singular closed real algebraic manifold. For this, we can apply implicit function theorem. And after that, we put the desired manifold as define the desired manifold by as large S, and desired function by the composition of the distribution of the canonical projection to the manifold and another canonical projection. And this is for pre-images of some points of R points in the region. For the map into the onto R. For example, in the case R is the interior of the unit disk, then we have a canonical projection of the unit sphere as this. Okay. And I want to remark some. Maybe there are some time. In general, topologically, we have so-called special generic maps as the maps onto the image closure of the domain. Special generic maps are generalizations of most functions with actually two singular points of spheres and canonical projections of unit spheres. They are very low to be nice classes of generics with mapping, knowing the topologies and the differential structures of the manifolds. By the definition, the manifolds and the maps are strongly restricted, and on the other hand, some manifolds regarded as elementary in some sense is, for example, such connected sum admit such maps in considerable cases. Thanks to such interesting properties, there are many studies on special generic maps. Okay. And additional remarks. According to a study by Bodin, Professor Bodin, Popescu Pump, and Soria-san, maybe she's here. For the other and she's that. She's also the speaker. For the wicked obeying in the plane and pancreatic graph of certain value class, we have a station as presented in theorem 2. Okay. However, we can't know the polynomial polynomials for the curves surrounding the domains explicit in general. As another debug, for a generic so-called generic graph, we have a most function such that the distinct between the values are distinct, and the Reeb graph is isomorphic to G. A suitable approximation presents a smoothly algebraic function. However, we can't apply this for graphs which are not generic. On the other hand, we don't use such technique and we avoid approximations and existence. Okay? And as another answer is this. We give L and M, small m and small m integer, positive integers and increasing sequence of length f. There are of length f. This FJ, this is a family of smooth closed manifolds such that there are sometimes unit spheres and sometimes collected sum of the products of two unit spheres. Collected sums. And under such a situation, we have a similar result. Furthermore, the singular set is finite, and this is the set. That sequence is the set of all singular values. And the pre-image is diffeomorphic to small fj for a point in the interval, open interval from tj to interval. And and comments, I want to comment on theorem 3. Okay. Main gradient of our proof of this theorem 3 is, in short, using technique of theorem 2 inductively. Okay. By using theorem 2, we can have a map on a closed manifold into the map into the domain. And we can also have another domain whose boundary is the obtained manifold and finitely many disjoint disks and disjoint spheres of fixed value. And that's really compose the canonical projection. This construction is the evaluation diffeomorphic to unit sphere or manifold represented as collected sum of two unit spheres. Okay. And this is a previous result related to the theorem 3. There is a okay. Small m be an integral greater than 2, and there's a graph, and on a graph there's a continuous function. And family of smooth closed manifolds available by H are given. And manifolds satisfy the condition. And then under this condition, we have a most function on some manifold. And the Reeb graph is identified with the given graph. And the pre-image is as prescribed. In fact, manifolds are more generalized there. Okay. Okay, I'd like to close that talk. And by future problems. First, can we extend our answers to problems of results to grades of either classes and cases conditions on pre-image more general. It seems to be difficult because the category is very strict. As another program for graph, what is the simplest and most natural smooth function whose Reeb graph is a graph in the manifolds? We may also need to pose suitable condition singularity, preimage, and the category. A kind of natural programs. And for a graph with exactly one edge and two vertices, the canonical projection unit of search seems to be an answer. Okay. Differences. Okay. Thank you for your listening.
Thank you very much for your talk. Are there any questions or comments? Yeah, if there is no question and comments, then we have next talk in 3 minutes. Maybe we can start now if you're ready.
Okay.
Okay, so our next speaker is
okay. Okay.
Our next.
Let's stop that. Thank you.
So our next speaker is Lukasz Michalak from Adam Mickiewicz University in Poznan, and his talk is titled Reeb graph invariance of morphs, functions, manifolds, and groups. Please.
Thank you very much. First of all, I would like to thank the organizers for their effort and for the opportunity to give this talk. In the previous talk, they were considered Reeb graphs for algebraic domains, but here I will consider smooth manifolds of dimension at least 2, and the smooth functions with isolated critical points, so with finitely many of them by the compactness of the manifold. I especially focus on Morse functions, so functions which have non-degenerate critical point. And in 1946, French mathematician Georges Reeb and later also Alexandre Cronrod introduced the relation whose equivalence classes are connected components of the level set of the function. And the obtained quotient space we denote by R of f, and it is called the Reeb graph or Cronrod-Reeb graph of a function. And for such a function with isolated critical points, this is in fact a finite graph, so one-dimensional finite CW complex, and its vertices correspond to connected components of level sets containing critical points. Here we see a classical example of a height function on the torus, and it's a Reeb graph, which has one cycle. For example, this red cylinder is contracted by the quotient map to this edge of the graph. And it should be noted that we can consider Reeb graphs for wider classes of functions. And for example, Psyche recently proved that if we consider function with infinitely many critical points, but with finitely many critical values, then also the Reeb graph is a finite graph. But Reeb graphs became more popular in the 90s, probably started by the paper of Shinagawa and collaborators, where Reeb graphs were proposed to use in computer graphics for morphing, coding, and comparing objects. And now they play a fundamental role in computational topology for shape analysis. And also the algorithmic version, the mapper, is a basic tool in topological data analysis, which was started by Singh, Pamori, and Carson. But Reeb graphs have also many applications to pure mathematics. They can be used everywhere where we would like to compare functions. So they are used in the study of the space of Morse functions, Morse bot functions, in singularity theory, foliation theory, even in differential equations. We also showed with Václav Marzantowicz that they have some applications in geometry group theory, the study of epimorphism of free groups. But now I would like to focus on the question what Reeb graphs can say about the manifolds a manifold itself, what topological properties of a manifold can be seen in Reeb graphs. So let us start with first basic property of Reeb graphs. It is the so-called good orientation of a graph. This orientation induced by a continuous function, which satisfies the following two conditions. First, it is strictly monotonic on the edges, and it has extrema exactly in the vertices of degree 1. And this orientation was described combinatorially by Charcot. And it is easy to see that any Reeb graph admits such a good orientation induced by a function to obtain by the quotient topology. And Charcot also showed that it is a specific orientation. There are graphs which do not admit it, as the one on the left. There are combinatorial issues which do not allow to construct such a function. But we add one edge, for example, here, then such a graph can admit a good orientation. So this is one thing. The second thing which describes graphs are its number of cycles, and it can we have some properties about this number of cycles from the following construction provided by Kaluba, Marzantovich, and Silva. So for a given function with isolated critical points, we can construct a graph gamma of f and its embedding if a manifold such as the composition with the quotient map is the homotopy equivalence of graphs, and in fact it contracts the trees on critical levels to the points, and it is bijective on the rest of the edges. And so from this we obtain that the quotient map induces epimorphism on fundamental groups. The fundamental groups of a Reeb graph is the free group of rank equal to the first Betti number of the Reeb graph. And so we obtain that this first Betti number of the Reeb graph, its cycle rank, is bounded by the corank of the fundamental group of the manifold, where the corank of the group G is the maximum rank of a free group onto which there is an epimorphism from a given group G. And the starting problem for my research was the following question: if we have a given manifold, which graph can be realized as the Reeb graph of a function, especially of a Morse function? So I would like to emphasize that we have a fixed manifold M, so it is a harder problem than if we would like to construct a manifold and a function. And realization can be up to value relation, up to isomorphism of oriented graphs, and it is still unsolved for higher dimensional manifolds. And up to also can be this problem considered up to orientation preserving homeomorphism of graphs. So we ignore vertices of degree 2, and also up to homotopy equivalence. So we have seen that the Reeb graphs have two necessary conditions: a good orientation and its cycle rank, its Betti number not greater than the corank of the fundamental group. And summarizing the realization theorem for Reeb graphs, we see that these two conditions are in fact sufficient to construct a Morse function on a manifold whose Reeb graph is orientation preserving homomorphic to a given graph gamma. And we can provide a complete classification of Reeb graphs for of functions on surfaces for up to isomorphism for various classes of functions, but for high dimensional manifolds it is harder to do. And the idea of the proof is the following. First, we need to construct a Morse function whose Reeb graph is in the so-called initial form, as we see on the left. And then we introduce the modifications of Reeb graphs, which are realized by modifications of Morse functions. These modifications comes from Morse-Hendon theory, for example, rearrangement and cancellation theorems, but we also need to use some other surgery constructions to obtain more complicated modifications of Reeb graphs. But having these modifications, we combinatorially prove that any given graph gamma with good orientation can be obtained by using these modifications from the initial graph. So this is realization up to homomorphism of graphs. And recently Saeki provided a construction of a function whose Reeb graph is isomorphic to a given graph gamma. But the function has, it has finitely many critical values, but it has infinitely many critical points. And in fact, these critical points form n-dimensional submanifolds. So these such functions do not reflect many topological properties of a manifold, and it can be seen also even for surfaces, because if you would like to realize a graph as the Reeb graph up to isomorphism, or as the Reeb graph of a Morse function, then, for example, for orientable surface of genus G, the number of vertices of degree 2 in the graph needs to satisfy the following inequality. So, yeah, we cannot construct any graph up to as a Reeb graph up to isomorphism, ignoring vertices of degree 2. So, yeah, it is still open for high dimensional manifolds. So, and in fact, the problem of calculating the number of degree 2 vertices in Reeb graphs is related to the other problem of finding an algorithmic method of calculating the Corank. It was proposed by many authors because this problem is related with the solving equations in the free groups. And for example, Stallings proposed to use systems of hypersurfaces, so the systems of codimension 1 submanifolds with trivial normal boundaries, but we don't know of such a method. And yeah, but in fact, there is such an algorithmic method of computing the Corank. This is the method of the so-called Markkanen-Rasborov diagrams, and they allow us to describe the structure of the set of homomorphisms from a given group G to the free group. But in fact, they are hard to use in practice in a particular situation. Yeah, it is hard to do it. So we can try to use Morse function as Reeb graph to solve this problem. And so the problem is how to find a function whose Reeb graph has maximum possible cycle rank equal to the Corank of the fundamental group. And so the function we call maximal, and Ki is the number of critical points of index I of a simple Morse function. And we can relate the number of degree 2 vertices in the Reeb graph with the number of critical points and the cycle rank of the Reeb graph. And from this, we obtain some lower bands for the number of degree 2 vertices in the Reeb graphs. The first one uses rank and Corank of fundamental group. The second one uses also homology group with ring coefficient R, and also the last inequality uses Lusternik-Schnirelmann category of a manifold. And these bounds are essentially different. And if we take a minimum on the left, we obtain the number delta 2 of them, the minimum number of vertices of degree 2 in Reeb graphs of simple Morse functions. Yeah, for surfaces, it is easy to compute. It is 0 for orientable surface of genus G and non-orientable of even genus. But for non-orientable surfaces of odd genus, this number is 1. We always have one vertex of degree 2 in Reeb graphs of simple Morse function. And yeah, and this number can be arbitrarily large, even with fixed dimension. So how to compute it? And let us see on the case of three-dimensional manifolds, and in this case, all these three bounds can be improved by the following one using Haggard genus of a manifold. And in fact, if we assume that function has only two extrema, then the number of critical points of index 1 and 2 are equal and are bounded from below by the Haggard genus. And yeah, a Morse function with minimum number of critical points is the one which has K1 equal to the Haggard genus of the manifold. And the following proposition shows the equivalence of three conditions, which shows that the equality in this bound with Haggard genus is equivalent to the statement that we can find a maximal simple Morse function with minimum number of critical. And in fact, if we take any simple Morse function, any, but with a minimum number of vertices of degree 2 in a Reeb graph, then it is automatically maximal and has the minimum number of critical points. So the question is for which manifold we have equality in this bound, and also in previous bounds. But let us focus on three manifolds and how to describe this number and or calculate it. And we can use the following methods from group presentations. Recall that we have a presentation of a group with n generators and n relators. Then its deficiency, the deficiency of a presentation is the difference, n minus m, number of generators minus number of relators. And the deficiency of a finitely presented group G is the maximum over deficiency for all presentations of a given group. And it is known that Epstein showed that for orientable closed free manifold, the deficiency of its group is always 0. And we introduce the following invariant omega of a presentation, which is the minimum number, such that in a given presentation, we can write first relator using first omega generators, second relator using omega plus 1 first generators, and so on. And this is then the omega invariant of a presentation, and for a given rank n, we can take a minimum over all omega numbers for all presentations of the same deficiency as G, and the rank equal to n. And also we can take the minimum overall all ranks of presentations obtained the omega of G. And how it is related with Morse functions and Reeb graphs. It turns out that we consider simple Morse function on orientable free manifold with one minimum. Then omega k1 of the fundamental group of free manifold is bounded by k1 minus the Fibonacci number of the Reeb graph. And in particular, the minimum number of degree 2 vertices in Reeb graphs of simple Morse function is not smaller than the twice of omega invariant of the fundamental group of a manifold. And for example, if we take a group G which is non-trivial, non-free, and torsion-free, then its omega invariant is at least 2. And so if we have a manifold with torsion-free fundamental group and with the difference between the Haggard genus and co-rank equal to 1, and Haggard genus at least 2, then this number of delta 2 of m is at least 4. And so we have no equality in the bound, dimension bound using Haggard genus, and so we cannot find a maximal Morse function with minimum number of critical points. And for example, it is the case for Heisenberg manifold, for which this number delta 2 of m is equal to 4. But yeah, there is no maximal Morse function with minimum number of critical points. So let us see on the non-trivial calculation of this invariant for circular bundles over a surface. These bundles are classified by the Euler number, is an integer, and the co-rank of such a circular bundle is equal, or the group of the circular bundle is equal to G. And if the Euler class is different, it's not generator, not plus minus 1, then the Hegel genus is 2G plus 1. And in fact, we have equality in our bank. So it has nice properties. We can find maximal Morse function with minimum number of critical points. But the question is, what is when the Euler class is a generator? Then the Hegel genus is decreased by 1, it is 2G. And it is the presentation of the fundamental group of such a bundle. And we need to use the following theorem, which is called Freiheitssatz. It is from PhD dissertation of Wilhelm Magnus. And recall that worded and free group is cyclically reduced if it is reduced. And yeah, the product of the last and first letter is non-trivial. And this Freiheitssatz states that we have cyclically reduced word in a free group, which contains some generator, and every non-trivial element of its normal closure also contains this generator. And yeah, using this, we may show that the omega to G invariant of the fundamental group of the circular bundle is equal to G. It is maximal possible. Okay, I need to finish, so maybe I skip the sketch of the proof. But combining these facts, this inequality, and that for this manifold, such a manifold, we have 2G, omega 2G is equal to G. We obtain a corollary that any simple Morse function with minimum number of critical points has no cycles in its Reeb graph. Any Reeb graph is a tree, and it has 4G vertices of degree 2. But it turns out that if we increase the number of critical points by 2, so another first step with decreasing the number of critical points, then we can construct a simple Morse function, maximal Morse function whose Reeb graph has cycle rank equal to the co-rank of the fundamental group, and in fact then we obtain the minimum number of degree 2 vertices, which is equal to G plus 2. Okay, thank you.
Thank you for the talk. It was very interesting. Are there any questions or comments?
May I ask a question, Dr. Michalak?
Yes, yes.
Yes. In your talk, in the last part of your talk, you consider a circle bundle over S2, right?
Over a surface, orientable surface of genus G.
Yes. And circle bundle. My question is more generally. How about more general Zeichert? How about for in the case of more general Zeichert manifolds and more general graph manifolds?
Generalization for graph manifolds, yes? Well, I understood. Yes. Yeah, I don't know. This is the next part of my research to investigate this for larger classes of free manifolds. For now, I don't know.
Thank you.
You need to unmute you.
Yes, there are no questions, right? So let's make a break for 4 minutes.
Thank you.
Hello.
Hello, please share your screen.
I would like to ask not to be recorded. I prefer to not record my talk if this is possible, please. Is it possible to not record?
I mean, I don't know, maybe Nadia. I don't know who records, but I think, yeah, we can not record you.
Right now I see it's recording.
Ми маємо запис. Ми маємо запис, можна просто далі працювати.
Вона має на увазі, що не хоче, щоб її записували.
Ірина, ми все записуємо. Ми все записуємо, а потім ми будемо викладувати це на YouTube.
А ми-
Я не знаю, як я можу дати їй можливість, щоб вона теж записувала. Ми можемо їй потім прислати ссылку на її відео, і вона зможе його там зробити, скачати.
Вона має на увазі, що вона хоче, щоб її не записували, просто нікуди не викладали. Можна зупинити тоді, чи просто...
It says allow to share.